Today we're discussing how to calculate Kb, the base equilibrium constant. We're doing this so we can predict the pH of weak bases. We want to be able to convert between OH minus, pH, POH, hydronium ion concentration, as well as being able to convert between Ka and Kb. So Kb works pretty much the same way as Ka does. Just like weak acids, weak bases react in equilibrium. So while we can calculate hydroxide ion concentration directly from the concentration of a strong base, we can't do that for weak bases. We have to figure out what the equilibrium will be. We have to use Kb in order to determine what the hydroxide ion concentration is. The Kb formula looks very similar to the Ka formula. However, we have replaced hydronium with hydroxide, and we now have the base on the bottom of the equilibrium law and the acid on the top. And in this case, that means that it's the Bronsted-Lowry base and the conjugate acid. Now, I am using HA and A minus because those are our generalized symbols for an acid and a base. Even though they're kind of orienting themselves towards the acid side, they still represent an acid and a base. And you will actually notice that in weak base equilibriums, a weak acid does get produced. Just like with Ka, this is often going to pass the rule of 1,000, so the change in the initial base's concentration will often be negligible, and we use this because it's an equilibrium reaction. So we are able to actually calculate a value for Kb if we know what the equilibrium values of everything is, or we can use Kb to predict the amount concentration of the hydroxide ion concentration in the end. Kind of the same way that we're able to use Ka and hydronium ions. If we want to calculate Kb from amount concentration, it's pretty much the exact same as calculating Ka or Kc in any other reaction. But what you have to be careful about is oftentimes when you're doing these problems, you'll be given a pH instead of a POH. So you've got to remember that pH can only calculate the hydronium ion concentration, and you don't want hydronium ion concentrations in this formula. Instead, you're going to have to convert the pH into a POH and use that to figure out what the hydroxide ion concentration is. You can then use that with an ice table to figure out what Kb would be. You can also calculate Kb if you know Ka. And this is very useful for us because if you look in your data book, you'll see that you're given the Ka values for all of the acids on the tables, but not the Kb values. But giving you the Ka allows you to calculate the Kb for the conjugate base as well. And this is really simple because Ka times Kb is equal to Kw, 1 times 10 to the negative 14. So if you know what Ka is, you can automatically calculate what Kb is for a given conjugate base. This also is why we say that the conjugate bases of the strong acids are not bases. The Ka for those numbers is extremely large, which means that the Kb for them would be something like 1 times 10 to the negative 50, which for all practical purposes would be 0. And as mentioned before, you want to make sure you're checking for rule of 1,000, and most of the time in Chemistry 30, it will pass the rule of 1,000. If you're dealing with a multiple choice or numerical response, I can pretty much guarantee that, unless you don't actually have to do any calculations to answer the question. Now, if you're doing a written response, you might have a change in concentration, so you'd have to use quadratic formula and show your work. But most of the time in Chem 30, Ka and Kb problems will pass the rule of 1,000s. You don't need to worry about them, so you can use that nice simple math where all you have to do is rearrange the formula and solve for x squared.